Welcome to Season 2 Purdue University College of Sciences Superheroes of Science podcast. I'm Stephen.
And I'm Sarah. We will be discussing anything and everything related to science. If you have a science question, tweet it to us at Purdue SOS, and we will try and find someone to answer it for you.
Joining us today on Superheroes of Science, we have Barbara Cohen. Barbara is a planetary scientist at NASA Goddard Space Flight Center. So welcome, Barbara.
I'm glad to be here.
Yes, we're glad we were able to connect with you. We're very excited.
Yes.
Saw some of the programs that you were working on, and we're like, ooh, this would be really cool.
I do have a very cool job right now. It's true.
So I was telling my family that we were going to interview you, and they're like, whoa, they were all excited. Telling them about the projects that you were doing and stuff. And so let's inform everyone else. What are some of the projects you've been working on?
I'm a planetary scientist. I have a geology background, and my PhD is actually in planetary science. So now I study all planets all the time. And my interest is in impact events across the solar system, how bodies have been whizzing around and crashing into each other, and when those happened, and what the effects would be on the different planets. So I use laboratory work. I do laboratory geochronology. Geochronology is time and Earth, so when rocks formed. So I do geochronology of when impacts happened. When an impact happens, it creates a big crater, of course, but it also can melt and vaporize the rocks, and that resets them in time. So we get to understand the time that those formed. And that interest has led me to also use avatars for my laboratory. So that means I don't get to go to the moon or Mars, but we have robots that go to the moon and Mars, and they can do those investigations for us. So I started using robots as avatar geologists when I started working on the Mars Exploration Rover's mission in 2005. And since then, I've gone on to work on Spirit, Opportunity, Curiosity, and now Perseverance to collect samples from Mars and return them to us. And my great love is for the moon. I would love to send a mission to the moon. The US hasn't sent a robotic lander to the moon ever since the 70s. So that's something that we're working hard on to return new samples from the moon, or to even just send orbiting spacecraft. So I have a spacecraft called Lunar Flashlight that will go in hopefully 2021. We're still waiting to hear when our flight will be. And that's gonna look at giant impact craters at the south pole of the moon. Those giant impact craters may have ice in them. That would be a really cool thing to use for astronauts if they wanted to maybe dig it up and drink it. But it also holds a record of bombardment in the solar system. So all of the comets and asteroids that have been hitting the Earth and the moon leave traces of themselves behind. And as those traces get caught in those polar craters, they leave a record of themselves and how many of them were hitting the moon and when that happened. So we use that as sort of a time capsule. I'm also sending a mass spectrometer to the moon. That's gonna be on a commercial lunar lander, hopefully next year. That is gonna be looking at volatiles in the lunar exosphere. That's its main job. But my interest is also in using mass spectrometers to do geochronology. So it's our first little foray into putting instruments on the lunar surface that will lead up to bigger payloads, bigger, more capable payloads to eventually do these kind of geochronology measurements on the moon.
Wow.
We've been taking notes because by the time I remembered a question, you had something.
Well, you said I tell you, so those are all the things.
Wow. Well, can I just ask before, so the mass spectrometer, because it's my understanding, is it common for a mass spectrometer to be used right now, like in the fields here on Earth? Or I thought samples were maybe collected and then taken back to be used in a lab with a mass spectrometer. So what's involved right now with having a mass spectrometer able to be used in the field, let alone on the surface of the moon?
Mass spectrometers are really, really common on spacecraft, on planetary spacecraft. So there's a lot of mass spectrometers flying on nearly every spacecraft that we send. Galileo and Cassini and lots of things have mass spectrometers, and that's because we can't bring those samples back to the Earth and analyze them in the lab. So you're quite right. If you have the capability to go get a sample and put it in the laboratory, those mass spectrometers in the laboratory are much more precise. You can use much smaller samples. You can really pick and choose the samples that you want to analyze. So that's what we do for meteorites. The only way we have mass spectrometry for Mars for a long time was to get those meteorites in our lab. But there is a mass spectrometer flying aboard Curiosity. It's called the Sample Analysis at Mars Suite, and that's actually run out of Goddard. And so it's analyzing both the samples that are drilled in Curiosity and also the atmosphere at Mars. So mass spectrometers have a wide range of applications and are really common flight components. What's not common is getting the age of a rock by using a mass spectrometer to investigate the rock itself. On the Earth, when we do this analysis for geochronology, you're quite right. You've seen those mass spectrometers in labs. They're huge. They take up enormous, space in the laboratory. They're very precise. You need, sometimes you need clean room techniques. You need to get at very trace amounts of elements to do geochronology. So what we're doing is developing that capability that would be less precise. That is true for all of our planetary measurements. When you do something in situ or you do it on a flight instrument, it's less precise than what you can do in a lab, but you're really trying to do a reconnaissance measurement or really trying to get at fundamental processes and not the super detailed work that we do in the labs. So it's just really asking a different set of questions, asking a broader question, trying to get a broader answer and an overview. So the mass spectrometers that we send to the Moon and Mars are smaller, they're more compact, they take less power, and you might not be able to prepare the samples the way that you would in the laboratory. But the alternative to that is bringing samples back from everywhere on the Moon or bringing samples back from everywhere on Mars. We have a Mars sample return mission being planned now. The whole thing end to end is going to take about $10 billion. So if we could do that 1,000 times, that would be awesome, but that is not what's going to happen. So we're trying to develop this capability to bring it to the Moon and Mars and asteroids and Europa and wherever else in the solar system so that we can do those measurements on the surface of the planet and get sort of our first order answers.
So 2 questions on that. Sorry, I cut you off, Sarah. Am I good? Okay.
Yeah, go.
One, what exactly is a mass spectrometer? How does it work, especially these remote ones that you don't have in a lab? How do they work? And what information are you gaining from them?
A mass spectrometer works when you let molecules into an inlet and then manipulate them with an electric field. So an electric field will you ionize those molecules so they gain a charge. So every one of those molecules has a charge. That charge is related to how tightly their electrons are bound. And that, of course, depends on the element itself. Every element has a unique electron arrangement around it and with a unique energy set of those electrons. So when we strip off an electron by ionizing it, now it has a charge and it has a mass, and that uniquely identifies that atom or molecule, the mass to charge ratio. So we can tell exactly what element we have, even what isotope of an element we have. So in order to measure that, we manipulate those ions with electric fields. When you pass a charged particle through an electric field or a magnetic field, electromagnetic field, you can manipulate its path. So that is what we do. We either manipulate its path or the length of time that it takes to get to a detector. So we manipulate the ions as they get to a detector, and we can measure their mass to charge ratio on the detector. And like I said, that's a unique fingerprint for every isotope and every atom that we can measure. So when we measure those on the detector, we can say, I have this many atoms of magnesium, this many atoms of silicon, this many atoms of potassium. And more than that, I can say that it's the isotope of potassium that has a mass to charge ratio of 40, or a specific isotope. So that's what we're measuring with a mass spectrometer, are the elemental abundances and their isotopic ratios. That's what we do in the laboratory. That's what we do on a planet as well. It's the same exact fundamental principle. Mass spectrometers come in a lot of flavors to be able to actually implement that measurement, but that's fundamentally what they all do. And the reason we want to do that is, for geochronology, is that we measure a parent and a daughter that tell us the time that elapsed. So we have a radiometric parent or radiogenic parent atom. So something that you know of, like uranium that decays, or thorium, right? Those are radioactive elements. They decay over time to daughter products. We use a system called potassium and argon. Potassium is a naturally occurring rock-forming element. You can see it as the pink mineral in your granite countertop. It's in your bananas, it's in your salt substitute. It's a very common element. It's in lots of rocks on the moon and Mars as well. And it has a very small radioactivity to it. It's not going to hurt you when you eat it, but we can measure that. So some of the potassium decays over time to its daughter argon. And we want to measure the amount of potassium and the amount of argon. And as time goes by, the potassium gets smaller and the argon gets bigger. So the ratio of that daughter to the parent tells us how long that rock has been sitting there on the surface, and that tells us what event created it. So that is fundamentally what we're doing either in the laboratory or on another planet, is measuring the parent and the daughter. And the way we measure the parent and the daughter is by ionizing the atoms in the original rock and then counting them and understanding their mass and their isotope ratios.
Oh, perfect. That was awesome.
Awesome explanation.
I'm glad you could understand it.
No, that was a great explanation. Great way of putting that. And so with these rovers, I mean, you've been, I mean, we heard a rover. We know what a rover means. But I thought it was interesting that you were using the term more of an avatar for that.
Yeah.
So is that NASA? Is that what you would at NASA more likely to refer to what we call a rover, avatar?
You know, there's a fun book called Thinking Like a Rover, and it's something that we used when we were working on the Mars Exploration Rover's mission. Those missions were designed intentionally to have human-like aspect ratios to them. So the mast was 6 feet tall. It had 2 eyes to take stereo. That's approximately what a human would see. And then it had an arm that had a microscopic imager. That's approximately what a hand lens would see, which is a tool that geologists use in the field to look at close-up images. It had a lot of other capabilities too, like seeing in the infrared that we don't have. But that's what geologists use them for, is to walk around on the surface of another planet for us and to take that data and send it back to us when we can't go there. So it takes data that we're familiar with. It takes data that we don't have personal experience with, but we know how to interpret. We can use all those data to really feel like we're there. And when we're using the tools, when the rover planners who actually implement the motion for the rover, when they're using their tools, it's not uncommon for us all to be in the room, you know, saying, well, what if we move the arm like this? And what if the rover looks like this? And you're really using your body to simulate the position of the rover or where the rock is. And actually JPL has developed a virtual what is it called? Virtual environment tool with a headset.
Yeah.
Where they project the data into an environment, and then you can use the headset to examine things, and people who have joined you in that environment can see what you're looking at when you say, I want to look at that rock and I want to look at this side of it. Right? You can walk around and you can point to exactly what you're trying to look at.
Oh, and those are really amazing headset too. It's not much different than Well, my glasses, really. It's not the big bulky ones that they do.
Oh, these are big bulky ones, but you know,
Oh.
I mean, relatively speaking, it's not a whole helmet or anything.
The ones I saw in the lab at Purdue when they were hooking in and they had the avatars of different people, they took screenshots. They were smaller and I could see through it when they put me on.
Yeah.
It kind of like the Google Glass. I think it is kind of like those.
Mm-hmm.
So that was kind of neat, although it really creeped me out because it felt like it looked like you were really on Mars.
Yeah, well, I'm really interested in how we can improve that feeling of being on Mars or being on the moon. To me, that's interesting for so many reasons. One is the scientific collaboration that can come with it when you have multiple people and you can really act more like a geologist and really see around things. That takes a lot more imagery than we typically get on a rover mission. We don't send the whole Curiosity rover 360 degrees around every rock in our path. We don't retrace our path. We don't set up a grid pattern to take a field of data. So we're not using the Curiosity rover in a way that enables a fuller virtual reality experience, because that's not what it's for. But you could easily envision, for example, the helicopter that's going to fly, or sending, you know, smaller sub-rovers that would take that kind of imagery and be able to project it into that kind of environment. And then making those tools available not only to the team, but to the public. You know, if you could loan out 30 of those headsets to a school group or something, right, and have them wander around in it, tell you what cool rocks they see. I think for the moon also, this is something that we're very interested in. The moon is only 3 seconds away in terms of light distance. With the rovers, we send commands up once a day, we get data down once a day. It's not a real-time interaction. It's just too far to be able to do that. The moon is far enough that it makes it tantalizing to want to do things in real time. But if you play video games or your kids play video games, you know, if you had a 3-second lag time, that's incredibly significant. It's enough time to drive a rover right off a cliff. So we can't necessarily do real-time joysticking on the moon, but you should be able to do something relatively close or something hybrid, where if you had that kind of environment, you should be able to interact with it much more readily. And I would love to see that happen. It's such an amazing platform. The technology's come so far that on all these landers and rovers that we're sending to the moon, we absolutely should be thinking about that.
With the moon, it kind of blew me away when I saw your Lunar Flashlight program. Because, I mean, I did not realize there could be frozen water. Because when I hear ice, sometimes like, oh, it is like methane, frozen methane. You know, what is this is frozen? But no, it's like you're talking about like water frozen.
Yeah.
I had no idea that would be on the moon.
Absolutely. That's one of the enduring mysteries of the moon. When we brought samples back from the moon with the Apollo astronauts, they went to sunlit regions on the near side and there was no water. There wasn't even any water in the rocks to the precision that we could measure it in the laboratories. So that's part of our hypothesis about what formed the moon. Is it formed in a giant impact with a lot of energy, and that energy would have driven off water, methane, ammonia, all those volatile compounds that we can think about, and they would have left the system, and then the moon would have accreted with dry material. So since then, and as our instruments have gotten better, we have found traces of water, but it's very, very, very small. So it's still consistent with this high energy event that drove most of those volatiles off. But then remote sensing has shown us that there is water at the very surface of the moon, but only in places where it's not sunlit. So the sun's energy will come in and it will derive volatiles off. It'll impart energy to those molecules and they'll escape from the low gravity of the moon. But there are places at the poles that never see the sun. And this is like in the wintertime, you probably have places on campus or near your house where in the wintertime, after a snow or something icy, where those patches are always in shade, right? The sun doesn't get to them because the sun in the wintertime is low to the horizon. And maybe your house blocks it, or maybe buildings block that area. So the sun is still going up and down, but there are permanently shaded spots where that ice just persists or that snow just persists. when you go to the poles of the moon, there are places that are like that year round because the sun goes around the horizon, but the craters are very deep. And so at the bottom of the crater, if you were standing there, the sun would be going around the horizon below the crater rim, and you'd never see the sun. It never goes directly overhead. And so those places only have enough energy that are coming out of the geothermal gradient of the moon, which is extremely small, and they don't have the sunlight energy to pop them off. So anything that collects there is going to stay there for billions of years. So anytime you have a comet or a meteorite that impacts the moon, it sets up its own little set of molecules. Most of those probably escape. Some of them probably bounce around and get caught. The solar wind actually, the solar wind is made out of alpha particles or hydrogen, basically. And the rocks on the moon are made out of oxygen, 50% oxygen by weight. So all of your standard minerals, you know, say MgSiO2, there's O2 right there. That's half of those molecules are oxygen. So when the solar wind hydrogen slams into a rock that's made out of half oxygen, you can get H2O molecules. And those can bounce around the surface as well and get caught in the cold traps. So those cold traps are places that record the history of billions of years of volatiles being delivered to the moon.
Oh,
It's
So
cool, right?
oh my gosh. Now, this is going back a little bit. Did I hear you use a term, exosphere? Is that a
Yes.
term? What is an exosphere?
That's a good question. The Earth has an atmosphere. Those are molecules that are gaseous, that are gravitationally bound to the Earth. They can't escape the gravity well of the Earth, but they exist in a gaseous state. So they've got a lot of energy and they're bouncing around and they exist as a gas. On some bodies in the solar system that don't have enough gravity to hold on to those molecules, they have what's called an exosphere. And an exosphere means that when a molecule pops off the surface because it gets enough energy from the sun, so say there's a particle of water, it gets some energy from the sun, it gets some thermal energy, and it wants to go away, but it doesn't get enough energy to escape the moon. It doesn't give enough energy to get escape velocity. That means it'll pop off, it'll take a little ballistic hop, and it'll settle on the moon again. And then when it gets more energy from the sun, maybe it'll pop off, take a ballistic hop, and settle on the moon again. So we have a lot of molecules that are doing that. They're popping off and bouncing around, but they don't encounter each other. There's not enough molecules for them to bounce into each other and hit each other. So that's what's called an exosphere. There are definitely gaseous molecules in sort of a haze or a cloud around the moon, but there's not enough of them there. They're not gravitationally bound in the way that an atmosphere is.
Wonderful. Thank you for explaining that. That's great.
and so are they not gravitationally bound due to the lower mass of the moon itself? Is that why they don't have the gravity there to hold an atmosphere?
So they are bound by gravity because they come back down, but there's not enough molecule-to-molecule interactions to hold them in suspension. So either they escape or they get bound back down. The conditions are not such that they can be in a gaseous state that hovers above the moon.
Okay.
So pressure, temperature, gravity, all of those things.
Okay. Images of sci-fi movies with terraforming came in mind there.
Yeah, so we do think that in the past, for example, when the big volcanoes on the moon were erupting, and you see those as giant lava flows on the near side, those were probably spewing a lot of gas at the same time, just like volcanoes on the Earth. So they're spewing water vapor and sulfur and carbon dioxide and all of those things. And that may have created a temporary atmosphere on the moon where those molecules were in suspension, more or less, and colliding with each other. And over time, some of them would have escaped and some of them would have condensed. And so they don't stay in the gaseous state. So temporary atmospheres may be a thing.
Oh, wow. That's so cool. Sorry.
The moon is cool.
Yeah,
It is.
we have learned so much about the moon of recent. I didn't even realize it was, possibly not just one solid dead rock. I didn't know.
Yeah,
Right,
exactly.
We just found out
Exactly.
a month
We
or
call it a planet because it's got a crust, a mantle, and a core, right? There's a dynamic definition of a planet that the IAU uses for observers, and then there's a geologic definition that geologists use, and that's did it have a crustal mantle and a core? Did it have lava eruptions? Did it have a magnetic field? All those things are really important to understanding how planets function, how the Earth functions, Mercury and Mars. But the moon did that as well. And so we use that as a natural laboratory to understand how planets function.
Oh, wow. That made sense what you said, but it's almost confusing. And because
Well, astronomers want to know like what relationship things have to each other when they're looking through a telescope. So yes, technically the moon orbits the Earth, and technically we both orbit the sun, right? So that is a dynamical explanation for the moon orbiting the Earth. But just because the moon orbits the Earth doesn't mean that it didn't have a crust, a mantle, and a core. So that definition sort of is useful for a subset of scientists. So I'm not going to argue about whether for them it's a useful definition, and that's great, and they can go off and use that. For geologists, a more useful definition might be, did it have enough gravity? Did it heat? Did it differentiate? Did it have geologic processes? That's more useful for us.
And so when we hear about the 8 planets or whatever in our solar system, that's just an astronomy definition of 8 planets.
That's an astronomy definition. And
or
that has
geologist,
to do with what is orbiting the sun as its own body, right? But when you know about things like Titan is a moon of Saturn that also probably has a crust, a mantle, and a core. It's got an atmosphere that's very much like the Earth. It has rainfall, it has oceans, it has canyons. How can you say that doesn't function like a planet? That totally functions like a planet, but it orbits Saturn. And so dynamically, it doesn't orbit the sun on its own, so it's not a planet in that sense. But we would for sure call that a planet. Pluto is another great one, right? It is part of the Kuiper belt. So it is part of a population of bodies that probably didn't coalesce to form a bigger planet. Same as the asteroids. A lot of big asteroids. We had this great Dawn mission to go to Ceres and Vesta. Ceres and Vesta also differentiated crust, mantle, and a core. May have had magnetic fields at some point. May have had lava flows at some point. Of course they're planets, but they are asteroids because they are in the asteroid belt. They're small, they're rocky. So you can have multiple things going on at the same time.
All right,
I really like that you look at those definitions then, and almost like to frame the questions that you're wanting to ask, or maybe that inspires some of the questions that you want to ask. I like using those. That's really cool.
Yeah, exactly. Exactly. It helps us frame why we do planetary geology. And you can't just work on things that are, orbiting the sun. You have to work on everything that functions the same way.
Yeah, I never would have, I guess, I don't know why, but I never would have thought that there were different areas of science would have different definitions for particular things.
It's not really a definition. And that, I think sometimes we get hung up on what a definition is. Mm-hmm. So, a friend of mine uses this: define a book.
Oh, well.
Is there a definition of a book?
I'm not sure.
Do you care? Do you care what the definition of a book is? When you're reading a book, do you care what someone defined it as? Does it have a hardcover or a softcover? Or does it have to be so long? Does it have to be, about something or not about something? Can it have pictures or not? Like, do you care? No, you don't. You want to read a book, right? So, getting caught up on definitions is not what science is. Science isn't about classifying things. Science is about using them to learn about the universe.
Oh, I love that.
Wow, I do too. That's awesome.
Yeah, it is. Okay, I'm looking at the time. I see we're about there, and I apologize.
No, that's okay. I don't have anything after this until noon, so however long you want to go is fine.
Sarah, did you have another one? I know I cut you off once.
No, I don't think so. I don't know. Gosh, I feel like I have a lot of questions. I don't know.
I know, that's my problem. That's my problem now. I have so many questions. I'm not sure what to ask.
Yeah.
You can go away and think about them, and we can talk again if you want, or you can.
Ooh. Oh, that's great.
we might have to, because I know I want to learn about the other projects more, but I keep these limited to about a half hour total, and so by the time we went into those, I think it would take a little too long.
Well, if you want to dive deeper into any of the specific projects, let me know, and we can talk about any one of them in specifics.
Excellent.
Oh, definitely.
Oh my gosh. Thank you so much. This has been awesome.
It's always a pleasure. You never have to twist my arm to talk about how cool the moon is. It's awesome.
Well, it was definitely educational. Heck, for me.
Yeah, me too. I know. It's always I love the all the different. I just feel like there's so many content areas all wrapped up in what you're doing. I mean, every time I hear someone talk, I think, well, that's everything. It's not just chemistry. It's not just geology. It's not just even math or programming. It's everything. That's just fascinating.
Yeah, it's everything. And then also, the practical working side of being a scientist it's also a lot of writing. It's a lot of sales to try and get proposals funded.
Absolutely.
Public speaking, trying to go to conferences and convey what you're doing. It's
absolutely
funny.
Because that's an awesome point of that. And I think a lot of students, I know, like in class, they would say, this feels like an English class, or this feels like a math class, but they don't when they're new to it, you have to be able to communicate what you're learning.
Yep.
Because otherwise, what's the point? I mean, if you're never going to share that information, why? So.
Yeah. And then, PIs also have to do, we have to do accounting, we have to do personnel management, we have to do all those things too. So, people come to science from all different walks of life, and some people are better at some parts of it than others, but that's okay. That's what makes science so rich.
Oh, I love that.
That's awesome. Well, thank you for your time. We really appreciate it.
Yeah, you're totally welcome. I hope to talk to you again.
Yeah, thank you.
Bye-bye.
Bye.
Take care.
Thank you for listening to our podcast.
Be sure to subscribe, rate, and leave a review.
An outstanding
on
review.
iTunes or your preferred podcast player.
Tweet us your science questions.
At Purdue SOS.
Until next time, be super, and remember,
You are someone's hero.
boiler up.
Hammer down.